This is lesson 6 in chaos, fractals, and dynamics based on the little book by Robert L. Devaney. And on lesson 5, we did some mathematics. We solved some equations. In particular, we were interested in finding out how we could find the fixed points on the curve, and in addition, we wanted to figure out how we could make predictions about the eventual 2 cycles. So actually, when we were finished with all that, we had a way to predict the eventual 2 cycles as well as 1 cycles or eventual convergence. Here's a little summary in this right up here. We found the fixed points by solving f of x equals x, which would keep it fixed because f of x equals x, x would equal to y. And then we, of course, f of x is always x squared plus c, so that meant we had to solve a quadratic equation. We got our solution, x1 plus or minus the square root of 1 minus 4c over 2. In order for that to have real solutions, and that's all we're looking at right now, x has to be less than or equal to 0.25 in order for the value under the radical to be greater than or equal to 0. Which means that for x greater than 0.25, we don't have a real fixed point, and so we have an escaping orbit. We're going to look at this now using a web diagram. Here's my web diagram, and notice I'm starting with a value of c of 0.43, and this is stepping off to infinity. The reason it's stepping off to infinity, one way to put it, is because there is no fixed point. The fixed point will occur when the curve in red intersects the x equals y line, the dashed line there. Here's our equation for the fixed point over here on the right. We'll notice d, which is the discriminant, which is the value under the radical, is negative, and that's why we don't have an intersection. We get an intersection as we drop c down to 0.25, and then right at 0.25 we have our intersection. Let's see if I can do that. There we go. And you can see it is in fact converging, although it's a little difficult to see. Now you say, well, it's not converged yet. We got 0.4, and it looks like our fixed points, we have 2 fixed points, notice, but in this case it's only 1, it's plus or minus, but it's because this is the square root of 0, there's only 1 at 0.5, and we haven't reached 0.5 because we don't have enough iterations. So we increase the number of iterations, we see we close in and get very, very close to 0.5, which is the value we have proven that we're asymptotically approaching as the number of iterations approaches infinity. Now to see this a little better, let's move our c down here to, let's say, negative 0.65, and you can see it is in fact homing in on our fixed point, which is negative 0.44868. Watch the last value here, which right now is negative 0.33 something. As the number of iterations increases, see how that value goes to negative 0.54 and just keeps on jumping around, but eventually homes in on negative 0.44868 approximately. It took 100 and something iterations to get it to 4 decimal place accuracy. So it's converging, but slowly. So this raises the question, why are we converging to what I'm calling xf2, fixed point number 2? What about this poor lonely fixed point up here, fixed point number 1? And the answer to that, we're not going to go through a proof of it, but the answer to that is the fixed point 2 down here is an attracting fixed point. The fixed point up here is a repelling fixed point. And we can get a nice illustration of that if we change our seed. Notice our seed in green down here is 0. If we change our seed and move our seed over close to the other fixed point, we would think that maybe we would go to that fixed point. But in fact, it's just like 2 magnets that are pointed at each other, and you're pointing the north poles at each other. They repel each other. In this case, this fixed point, as the other point comes closer to it, repels it and drives it to the attracting point. If we go beyond here, it just takes off once it gets over here. Notice if we go back over here, we're always converging to the fixed point that is attracting. If we get too far out, we leap over there to the right of the repelling fixed point, and then we don't get attraction anymore. So the concept of attracting and repelling fixed points is going to be something that we'll come back to later that's going to be fairly important. But right now, we're really only interested in the attracting fixed point. By the way, the repelling fixed point, if you actually plugged in the value, in other words, if you started with a seed equal to the repelling fixed point, then it would stick on that because it is, after all, a fixed point. Okay, the next thing we did, let's take a look at that. So negative 0.75 is going to be the boundary line, and it actually still at that point with a seed of 0, we do have eventual convergence. So it really is a 1 cycle. It's not a 2 cycle yet. I may have said that it was a 2 cycle last time, but that's so I misspoke. It's just it takes it a long time. Notice I've got 2,000 iterations here, and we still haven't reached the value of negative 0.5, but we're closing in on it. Which raises the question, well, what happens below negative 0.75? And we showed that it is an eventual 2 cycle. And I want to go there right now. And you can see it's oscillating between those 2 points, neither of which is one of the fixed points. And let's go and look at the math of that again. Here we are. Okay. So we were interested in showing the 2 cycle region, starting at C equals, and we wanted to show that it started at negative 0.75, which would mean every 2 iterations you get back to the same number, which means if you start with x, and you apply the function, and you apply it again, you get back at x, and that's stated mathematically right here. And then we plugged in for x, we plugged in x squared plus c, and when you apply f to x squared plus c, you get this. We multiplied the whole thing out, rearranged, got down here with this x to the 4th, and that's a quartic equation, which seemed like it would be hard to solve, but we know something. If you have a 2 cycle, then that also means that the 1 cycle, single cycle, since it doesn't change the fixed point, it repeats every 2 as well. And we'd already solved that. We'd solve that by taking the equation up here, x squared minus x plus c equals 0, and solving that, which means that x squared minus x plus c is a factor of our quartic equation, which means if we divide that into our quartic equation, done right here, if we do it right, we'll know whether we've done it right because we'll get a remainder of 0. And we did that using good old long division. And this was the answer we got. And that's our other factor. And the original factor, x squared minus x plus c, gave us our 2 fixed points. This factor, if we set it equal to 0 and solve, that's going to give us our oscillating 2 cycle numbers. And so we plug into that. And we solve. So we set it equal to 0 and we solve. We plug into the quadratic formula. We get this. Notice under the radical we now have something different, and we want that to be greater than or equal to 0, so it'll be real. So we set that to be greater than or equal to 0, and we solve for c, and we learn that for c is less than or equal to negative 0.75. That's where we're looking for a 2 cycle orbit. Now actually the actual point where c equals negative 0.75, we get x equals negative 1/2. We only get one answer there. So that's the answer that it's homing in on. So it's an eventual 1 cycle there with very slow convergence. Below negative 0.75, we have an eventual 2 cycle orbit, which really means the second fixed point is no longer attracting, because now we're being attracted to those 2 cycle numbers. So let's take a close look at that again here. All right, here we are. We're below negative 0.75. We do in fact have a 2 cycle. We can change those number of iterations. And as we change them, watch the values, oscillating between about negative 0.03 and 0.96. And see, here are our numbers down here. These are our 2-cycle numbers. Up here, our fixed points, we're not homing in on them anymore. They are both repellers, essentially. We're not attracted to them anymore. Instead, we are attracted to the 2-cycle. And you can see by just 647 iterations, we're certainly in pretty good shape and getting close to our answer. So that's a graphical illustration of what we did last time, as well as a nice write-up of it here. And again, I wanted to correct what I said before. Negative 0.75, I believe I said was a 2-cycle. It's not. It's the boundary between a 1 and 2 cycle. You do in fact get convergence there, but it's very, very slow convergence. Okay, so that's all we'll do for this lesson, which is essentially just a review of the previous lesson, but looking at things graphically and also giving you a nicer write-up. So we'll look at some, I think the next time we come together, we'll try to get a better picture of where things, in fact, do bifurcate. So what we're gonna look at is right now the way we're doing it with our graph over here, our web diagram, we change the value of C and we look and see what happens. And what I want to do, instead of changing the value of C and looking at what happens for specific values of C, I want to show you a way we can look at every value of C that's important and see the results all in one picture. So that's going to be our goal for next time.